That's people are using that now. They're using that in English to say mirroring means identical instead of a 180-degree reflection. Yeah. That's a new usage of the word.
It is interesting.
It takes a while for the outdoor.
Yeah, I had some of those in like middle school, and I didn't like that at all. That aspect specifically.
Brad Pierce is such a shining light. I need these.
Need your sunglasses.
Shades.
SABRE, is that like a, I don't know French, that's like something really good probably. To salute, SABRE.
Sabre.
Savor your science.
We're ready whenever.
Okay.
Yep.
Welcome everyone. I hope that everyone is having a great day. Today, the speaker for today is Brad Pierce. He began serving as the director of the Space Science and Engineering Center at University of Wisconsin-Madison in 2018. Prior to this appointment, he was a physical scientist at the NOAA and NESIS Center for Satellites Application and Research, and SIMS here in Madison, and senior research scientist at the NASA Langley Research Center's Atmospheric Science Division in Hampton, Virginia. He has more than 25 years of experience in the design, development, and execution of global atmospheric models, and more than 3 years of experience in chemical modeling and forecasting support for NASA, NOAA, and NSF field campaign. So without further ado, let's just go ahead and start with the presentation.
Thank you. So what I'm going to talk about is some very, very recent work that I've been doing with my two students, Maggie Bruckner and Gerald Acton. And this involves flight planning and chemical forecasting for a campaign called SABRE, Stratospheric Aerosol Processes, Budget, and Radiative Effects. So this is very, very recent. The final transit flight back to Houston for the WB-57 aircraft was on Monday. Maggie and I spent the weekend working on doing flight planning for that transit from Fairbanks, Alaska down here.
If you want to unmute your mic.
So this is a photograph that Maggie took up in Fairbanks, Alaska, and you can see the northern lights. This is also this is within the Elson Air Force Base, slightly away from the runway, but you can get a sense of how remote this deployment was. We were at an Air Force Base that was about 25 miles from Fairbanks, about 10 miles to the nearest town, which was called North Pole. My main memory of the field campaign is that the food was really bad at the Air Force Base and everything shut down at 7 p.m. So that's one of my main memories. Anyway, the motivation for the SABRE field campaign is very much policy relevant research, and it's controversial research. So the first part of this talk is I'm going to provide a context for why we're making these measurements, and then I'll talk about what we did specifically to help support those measurements. So there's growing concern among scientists and policymakers that climate change mitigation, what we're doing as a country and as a world, will not be adequate to forestall the more than 2.5 degrees C warming and potentially catastrophic sort of changes in our climate. And so these may occur more quickly and we may have serious impacts. So there is motivation for looking at other ways to deal with this potential catastrophe. Climate intervention, also called climate engineering or geoengineering, refers to deliberate large-scale actions intended to counteract aspects of climate change. And that's a very controversial topic. Climate intervention falls into basically two different categories that are kind of summarized with this schematic: carbon dioxide removal and increase in sunlight reflectance, or what's referred to as solar geoengineering. So these gray lines down here are the carbon dioxide removal approaches that are being considered. And they're, they involve seeding of the ocean with either iron or additional nutrients so that you sequester more carbon, adding additional forests and reforestation so that you sequester carbon in that way. Various other approaches, including direct capture and things like that. These are all possible scenarios. Some of these, each of these has its own advantages and disadvantages. On the other side is to just reflect more incoming solar radiation. Two main approaches. One would be increase cloud reflection by seeding maritime clouds. The second one is introducing additional aerosols into the stratosphere so that you reflect more sunlight, very much in the way that volcanic eruptions do within the natural Earth system. So to kind of schematically illustrate this, so this is climate impacts versus time, business as usual, which is no reduction in emissions. This is an aggressive emissions cut, which keeps us hopefully at a level that's sustainable. CO2 removal actually allows us to curve that trend back down, and climate intervention is able to accomplish that on a shorter time scale. So it's really considered to be a short-term response to trying to deal with climate change when it reaches a point, prior to when it reaches a point of no return. The National Research Council in 2015, to summarize their climate intervention, particularly the solar geoengineering, should it ever become important for society to cool the Earth rapidly, albedo modifications, in particular stratospheric aerosol injection, and possibly marine cloud brightening, are the only ways that have been suggested which could potentially cool the Earth within years of deployment. There's a lot of issues that are geopolitical that have to do with both of these. Particularly the marine cloud brightening. If you look at where the marine stratostacks are, many of them are in the southern hemisphere, and so you're changing the characteristics of marine clouds in the southern hemisphere, an area where the population largely is not responsible for the CO2 emissions that we're trying to mitigate. Stratospheric aerosol injection obviously has a much larger impact. We know that the stratosphere, and in particular the stratospheric ozone layer, can be very sensitive to aerosols, and so we need to make sure that each one of these mitigation approaches has potential negative impacts that we need to understand. And so in 2015, the National Research Council concluded climate geoengineering has often been considered a last-ditch response to climate change, to be used only if climate change damage should produce extreme hardship. Although the likelihood of eventually having to use these approaches grows with every year of inaction, there's a lack of information on ways how we can possibly do this climate intervention. Step forward to 2021, National Academy of Sciences, again looking at solar geoengineering. And this report at this point concluded that we need to have a strategic investment in research to enhance policymakers' understanding of climate change response options. And specifically, they say the United States should develop a transdisciplinary research program in collaboration with other nations to advance understanding of solar geoengineering's technical feasibility. And that this program should operate under robust research governance. It should include research code of conduct because we are talking about geoengineering, and it should be inclusive of public and stakeholder engagement processes. So this is very much policy relevant research. Congress in 2020 directed NOAA to lead a multi-year research program called the Earth Radiation Budget, since fundamentally we're talking about changes in the Earth radiation budget, to look at natural and human activities that might alter the reflectivity of the stratosphere and the marine boundary layer and the potential impact of those activities on the Earth system. The SABRE field campaign is focusing on increasing the amount of stratospheric aerosols. And fundamentally, it's collecting measurements of the natural stratosphere so that we can understand what the consequences of any additional injection of stratospheric aerosols would be. I'm not going to talk about the marine cloud brightening part of this. So that is the motivation for the SABRE field campaign. And again, you know, we can talk during the discussion about what the policy implications of this are, and I think those are discussions that we should have. But the key here is that this is very much at the direction of Congress, policy relevant research. So this is kind of a slide that summarizes what we need to understand about stratospheric circulation and aerosol processes to be able to really constrain stratospheric aerosol abundances. So I'll spend a little bit of time going through this because it kind of provides the key motivation for what our responsibilities were for flight planning. So if we get down here, we've got all sorts of biogenic emissions from the ocean that produce SO2, and SO2 then can produce sulfate aerosols within the troposphere. That is something that, particularly the anthropogenic emissions of SO2 from power plants, was what was causing significant air pollution problems in the United States in the 80s and 90s. Regulations have reduced those emissions, particularly from power plants, and now we have very little sulfate aerosol pollution within the continental United States. So that's a case where policy relevant research has led to reductions in emissions and improvement of the atmosphere. There's some species though, like OCS, which actually have very, very long tropospheric lifetimes, which means that they can get injected through tropical convection and they can get into the stratosphere. And then they can actually move well up into the stratosphere, and they become a source of sulfate aerosols in the stratosphere. OCS is both natural emitted and it's emitted from biomass burning and also from industrial activities. It's got a long lifetime. It's well mixed in the troposphere. It gets photolyzed, or it gets oxidized up here, it photolyzed and produces SO2, and then that can lead to sulfuric acid and sulfate aerosols. This transport process, there's two different circulations here in the stratosphere. Here's the tropopause, so this is the tropics, this is pole, so here's the tropical and mid-latitude tropopause. This is the Brewer-Dobson circulation. There's two main paths. One of them is this ascent, largely isolated ascent within the tropics, and then descent down within the polar vortex. This is a long-term circulation pattern. Air entering the tropical stratosphere here takes about 5 to 7 years to end up in the polar vortex, or in polar latitudes. There's a more direct route, which is this lower branch of the Brewer-Dobson circulation. And here you can get air that entered the tropical stratosphere into mid-latitudes at a much shorter time scale. So thinking about the time scales of transport within the stratosphere are very important, because any intervention would be injecting precursors or aerosols here, and then they get transported around.
The old question of what would the union layer be like without volcanic eruptions? What do you think about the percent of sulfur up there? Is it 10% OCS or less, including volcanic eruptions?
Yeah, so that they do. There's very long-term records of stratospheric aerosols, and there's debate about what the true stratospheric background is, because you keep having these perturbations from volcanic eruptions. We have perturbations from wildfires that are introducing organic aerosols into the stratosphere too. But so fundamentally the SABRE field campaign was to try and understand what are the main sources and sinks of aerosols in the stratosphere, in particular looking at this natural OCS. We also sample the rocket plume. So the other things that they're looking at are how much do rocket launches contribute to stratospheric aerosols. Meteoric smoke. There's instruments on the WB-57 that actually do single particle composition analysis, and we observed particles from meteors in the polar vortex during this campaign. So there's a number of different sources, and understanding what the dominant process is pretty much what the focus of this campaign was. There's a lot of instrumentation that's been developed so that we could make these kind of measurements in the stratosphere. And these are new instruments. The concentrations of these species are quite low, and so it's a very difficult measurement to make, unlike the concentrations in the troposphere. So that's kind of a big picture. From a flight planning perspective, the WB-57 can fly between about 14 kilometers and 17 kilometers. So the first part of it was out of Houston. We were trying to look at this entry region and characterize that. The second part of it was in the polar vortex, and we're looking at this aged air coming down. So this is kind of the overarching goals of the SABRE mission. Again, to advance our understanding of the composition, chemistry, and dynamics of the stratosphere and its impact on the climate system. I won't go through these in detail, but kind of the key thing, what are the direct radiative effects of stratospheric aerosols? How can we use in situ measurements to evaluate and improve stratospheric measurements of aerosols? Again, the longest record of stratospheric aerosols are from instruments like SAGE, which is making solar occultation measurements of aerosols. And then finally, using these measurements to constrain and improve global model predictions of stratospheric aerosols so that we have the tools that we can test impacts of potential climate intervention. This is the WB-57. Last week we heard a seminar about winter storms with the NASA high altitude ER2. I think of the WB-57 as the ER2 on steroids. Can't go quite as high, but it can go further. So this is the WB-57. I'm not going to go through all the instruments, but it was a well-instrumented aircraft. We've kind of been focusing on looking at N2O, because N2O is a good measure of age of air in the stratosphere. N2O is emitted at the surface. It's a radioactive climate gas. It gets photolyzed as it moves up into the stratosphere, and you can use the concentration of N2O to identify old air. In addition, measurements of OCS, carbonyl sulfite, which contributes to formation of stratospheric aerosols. Again, one of the key observables that we want to capture. And then all sorts of particle analyzers. The PALMS next generation, SP2 is measuring black carbon, and so on, as well as a fairly complete suite of gas phase chemistry measurements. So what did we do in the field? We provided forecasting support and flight planning during the 2022 test flights, which were out of Houston, Texas. And Gerald Octon and I were in the field to do those flight planning and forecasting. And then the 2023 SABRE mission, which was first in Houston, sampling the tropics, and then went up into Fairbanks, Alaska to sample the poles. And Maggie Bruckner was with me in the field for that part of it. What we're using is our real-time air quality modeling system, or RACMS, which is global chemical and aerosol forecast that we combined with ensemble trajectory-based diagnostics so that we can help interpret what the histories of the air that's sampled by the WB-57 is. This is the first time we've used RACMS to forecast for a stratospheric field campaign. RACMS has been running continuously. We've used it extensively for tropospheric field campaigns, but the stratosphere had basically been initialized, and except for ozone, largely neglected since 2010. So for me, it was my first chance to look at how well the RACMS stratosphere was doing from a forecasting perspective. As far as post-mission analysis, again, the transit flight just finished on this Monday, so the data is still very preliminary, and we're just beginning to start wrapping our heads around it. We'll be using Rackham's global chemical and aerosol analyses combined with these ensemble trajectory-based diagnostics, in particular something called reverse domain filling, to characterize the history of the air parcels viewed by the W-57. And then finally, these analysis products will help the instrument PIs interpret the WB57 measurements by looking at the large-scale distribution of these trace gases and aerosols and what was their origin, 5 to 7 days prior to being sampled by the WB57. And I'll show some examples of that towards the end of this talk. So this is the 2022 test flights out of Houston, Texas. Gerald and I are right there. Those are the pilots of the WB57. This aircraft is flying at 55 to 60,000 feet above the majority of the atmosphere, and so they're wearing spacesuits when they're flying this aircraft. And this is our 2023 deployment to Fairbanks. So this is when Maggie and I were up here. This is basically, there's the entire flight planning and forecasting team for this field campaign. And actually these two were swapping in, so most of the time there's really only 2 or 3 people doing the flight planning, which means that when I was up there, I was able to plan for 5 flights, and then Maggie and I had an overlap where we were kind of transferring how to do things. The week I left, Maggie forecasted for 4 flights in 5 days, and that keeps someone extremely busy. But you get really embedded in what you're doing, because you're not only forecasting and flight planning, but then the aircraft is in the air, you're looking at measurements in real time, and being asked by the mission scientists, should we dive now? Should we continue this track? How do we optimize the measurement? So it's a very immersive, but also a very intense kind of activity, something that I would recommend to any student. So anyway, so there's the W-57, there's part of the forecasting team, there's me being attacked by a bear. This is Maggie in Denali. She did take 1 day off, right, in 3 weeks, and was able to go to Denali, which is again a great experience. And she certainly looked happy to be in Denali.
Denali's taller than that.
Yeah, that's not Denali. Denali was clouded in, as it always is. This is Maggie walking from the hotel to the hangar, and I'd say maybe 25 below zero on that day.
Possibly.
Yeah.
Yesterday it had some wind.
Had some wind, so it's pretty cold up there. Cold enough that they didn't really want very many people renting cars, because you're likely to have those cars stall out some 30 miles from the nearest town, and so we walked from our hotel to the hangar every day, and people had to have the appropriate gear to do that. Okay, so Rackham's includes real-time assimilation of measurements, ozone measurements from the ozone monitoring instrument and the microwave limb sounder. So we have a very good strain on our prediction of ozone. Every day we assimilate measurements to initialize that model. We have less constrained predictions of our aerosols. We assimilate total aerosol optical depth from MODIS on both Terra and Aqua, but the total aerosol optical depth is basically reflecting tropospheric aerosols. How much that constrains stratospheric aerosols, which the optical depths are a small fraction of the tropospheric optical depth, is very little. So we're looking at a pretty unconstrained forecast of stratospheric aerosols. The other thing that happened during this deployment was a major sudden warmth that was happening beginning prior to our deployment, and significantly impacted our flight objectives during our deployment. So this is a figure from climate.gov showing 10 millibar temperatures from 60 to 90 degrees north. These are the outliers, warmest and coldest. This is the mean, and this is the 2022-2023 winter. So you can see we progressed with kind of colder than normal polar stratosphere up until January, and then we have this dramatic increase in temperatures associated with sudden warming. There's been earlier seminars talking about how sudden stratospheric warmings are first very hard to predict the actual onset of them, but once they have occurred, they increase the predictability of tropospheric weather. And I think that while we were up sampling chemistry within some of these vortex remnants, they were significantly impacting California weather because each one of these vortex filaments is also has a lot of vorticity, and those are driving a lot of the weather that we experienced during March of this year, particularly on the West Coast, an area that we need to look into more detail. So this is the model prediction, 30 kilometers, about 10 millibars, ozone on this panel, and N2O on this panel. And this is, in the beginning, we have a well-defined polar vortex with low ozone and low N2O because of air descending down from the upper stratosphere and mesosphere. High ozone and high N2O in the tropics because of that upwelling motion. But as the sudden stratospheric warming proceeds, you can see that this polar vortex gets ripped to shreds, that we've actually got tropical ozone that's coming in over the pole, tropical N2O that's coming in over the pole, and towards the end of this loop, we really have no identifiable vortex at 10 millibars. That vortex slowly starts recovering radiatively after the warming, but really is not going to reproduce until there'll be a final warming, that will end the polar vortex. So having this warming going on was a challenge for us because typically this is a wave one warming. Wave one warmings tend to be associated with an amplification of the Aleutian high, pushing the vortex off here, and we're flying out of there. So nature does its best to avoid detection. And that was a challenge for some of the flight planning. So what we did in the field is we produced these reverse domain filling predictions. They were initialized at 0Z each day. And then we provided forecasts for day 1, day 2, and day 3 at 0Z. These RDF calculations are an initialization of a huge set of back trajectories, flying those back trajectories through our Rackham's chemical analysis, and then computing Lagrangian averages along those trajectories. Once we have those Lagrangian averages, we can then remap those Lagrangian averages back onto the initial grid of trajectories, and we're left with a synoptic forecast of what the previous evolution of that air mass was. And that's useful because we can look at Lagrangian average descent rates, ozone production and loss rates, convective cloud mass fluxes, and all sorts of things. The other thing that it does is it takes a fairly coarse, Rackham's is a 1-degree model, and because you're doing back trajectory sampling, you sharpen up features that would be otherwise fairly coarsely resolved by the model. This was first developed in the early 90s where they used it for coarse, grainy satellite data. We're able to show that you can sharpen and amplify vortex filamentation processes in the stratosphere. We're using that capability to help improve the accuracy of our forecast. So this is now a loop. We're zooming in. Alaska's right here. This is the range ring of the WB-57. This is at 50,000 feet. This is the Lagrangian average ozone, and this is the Lagrangian average NO2. This is once per day for the month of January. This cutout right here is restricted zone because it's Russian airspace. And so basically our responsibility as flight planners and forecasters was during this period of very high dynamical activity is identify targets so that in the polar part of this, so that we could sample this aged polar vortex air that was associated with descent from the mesosphere. Ozone is high. In general, at this level, we're down below that 30-kilometer altitude. It's high in the vortex. But we were primarily using N2O as our tracer to identify these old air masses. During the test flights in 2022, we had opportunities to evaluate the fidelity of our model. We found out that the N2O prediction was not accurate in the stratosphere because we accumulated a lot of transport biases. So we did a bias correction using MLS observations on January 1st of this year, adjusted the model, and then let the model N2O continue forward and use that for the forecasting period. So this is a bias-corrected prediction of N2O. Anyway,
Is that a clue about anything, about advection or chemistry or anything?
I think it's a clue about, it's a clue about the Rackham's model top is not very high. We don't have very many stratospheric levels, and so we're not resolving that Brewer-Dobson circulation. We have too much tropospheric air, tropospheric type air in the lower stratosphere. So that was one thing. We did find other things that I'm not going into here. Our NOAA budget is off by a factor of 5. It's off by exactly a factor of 5. So we need to go look into that. But yeah, it's because the model had been running for 13 years with kind of a free running stratosphere. So anyway, we bias corrected it.
Hey, Brad?
Yeah.
What's with the change in color on the left side?
Oh, I think I go from, I think,
Oh,
2 to 3.
I see.
These are
Color
a
scale
real-time
changes.
forecast.
Got it.
You're right. I didn't remember which day it did that. It starts out as 2 and it's all red, right? And then it goes to 3 so you can see structure in there.
That makes sense.
These are our
I didn't
real-time
see the scale.
forecasts.
Yeah.
Other people, earlier on we did, you're in the field and the measurement PIs say, I can't tell what your units are. Could you make bigger? This is what you spend half your time doing, is improving your figures. But anyway, so this is what's going on, a very dynamically active period. If you look at N2O, earlier on in the forecast period, the polar vortex was sitting over here all the time, and we had very little opportunity to sample it. There's a period of about a week or about 4 days where the polar vortex lobe moves into the field of operations. That's why Maggie forecasted for 4 flights in 5 days, because it was our opportunity to sample that vortex lobe. Okay, so these are all the flights. 19 different flights. This is the Houston phase. This is the Fairbanks phase. And again, we were kind of key input into flight planning for each one of those flights. I'm going to focus on just one today. So this is a RDF forecast for March 5th, 2023. This was a really exciting one for me because I'd written a lot of papers back in the 90s about mixing processes in the polar night jet, and this is a perfect example of this. So here's a lobe of the polar vortex out here, well outside of our range ring, and here's this filament, narrow filament of lower N2O and higher ozone that would be a potential target. It was the best target that we'd seen in the last 3 or 4 days. And so deciding on a flight track to sample this vortex filament, which by its very nature is very unpredictable. These vortex filaments occur through chaotic advection. So small differences in initial conditions lead to large differences in where that filament goes. So it's a hard forecast challenge. Anyway, we wanted to try and target it. This is at 50,000 feet. At 40,000 feet, this is looking at dust predictions. There's an intrusion of dust from the troposphere into the lower stratosphere associated with this ridge right here. So we basically got this vortex filament here and a large dust intrusion here. We can kind of capture both this upper branch of the Brewer-Dobson circulation, sample that old vortex air, and this lower branch where you're looking at fairly recent injection of aerosols into the stratosphere. So those are the kind of flight planning and forecasting challenges that we had every day. And that's what makes being in the field really exciting.
Right, that seems like a pretty remote place for dust. I don't know if these concentrations, how they stack up against other things.
Yep.
Where did that come from? Gobi Desert or something?
This is, and I'll be showing some reverse domain filling things. It did come from the Gobi
Oh.
Desert. Yes, so this was, when we're out of Houston, most of the aerosols we were seeing were biomass burning aerosols, and they were coming out of South America. Convective lofting of biomass burning in South America. During here, I mean, associated with all of this disturbed stratosphere is very large amplitude waves in the Pacific, right? And so we were seeing dust transport, fairly significant dust transport coming from Asia. And it's, you know, when the aircraft is sampling that, that's exactly the question that they need to know is where did this come from?
Yeah.
So, and that's where we determine. So this is the flight track for that day. We designed something that's going to sample that dusty intrusion, and we designed something here that's going to do its best shot at trying to sample that vortex filament with the understanding that the actual prediction of the vortex filament location is we don't have high confidence in that. So what we do then is we take our model and we iterate this for over 2 or 3 days. We start with a day 2 prediction of what we think it's going to look like along the flight curtain. This is the day 0 curtain, so this would be the day of the flight. With the flight planners, we go in and decide what altitudes the aircraft should go at along this trajectory. And again, our dust forecasts and our ozone and N2O forecasts played a key role in flight planning. So this is this part where we're going to do a bunch of profiles through this dusty layer. This is the tropopause. Here's the tropospheric dust loading, which is beyond the scale. But you can see there's this detached layer where there's actually very, very clean, low aerosol air with this dusty layer above. And then if we go over here, this is where we're going to be sampling that vortex filament. So this is the prediction for N2O. And again, we're going in and out of this vortex filament, trying to optimize our ability to sample that.
See, that seems like a new paradigm to me. You know, you hear about fire, smoke, and other stuff, but not, like, that's in the stratosphere, not in the aerotroposphere.
This,
That does layer.
yeah, well, it's straddling the tropopause. So this is the tropopause.
Yeah.
There is some residual enhancements in the stratosphere.
Oh, I thought that was the white stippling was the layer of dusty intrusion.
No, the colors are the dust. This white stippling is actually wind speed, and then the dashed is potential temperatures. So these are the dusty air,
Oh.
and they're kind of, they are being transported poleward from the tropical tropopause. And we actually saw remnants of that ending up over the poles during some of these flight legs. So this is N2O, and there's ozone, and then here's our verification. So when we're forecasting, particularly for a fairly not a lot of observables to do the flight planning, you need to establish some confidence in your prediction. So one of the things we do is as soon as we get the flight data, which is typically 24 hours or so after the flight, we do a verification. So this is our prediction for ozone. Again, the measurements here in black, and these are all preliminary field measurements. The instrument PIs allowed me to show these for this talk, but it's not publicly available yet. And you can see that we capture the overall features fairly well. We capture generally some of these plumes. We underestimate the peak ozone in this region, but highly correlated. The bias is 10% or so. And this is N2O. Again, we're missing some fine scale structure, but we're capturing the general features. And again, we're showing that we would target low N2O, which is associated with aged air in that vortex flow. And this is carbon monoxide. Again, carbon monoxide is oxidized too, so it's low in the old air. This, we're looking more at how it's sampling as we move up and down across the tropopause. And again, we get fairly good agreement. So we have confidence that our forecast has skill. So this is the last part of my talk. This is how we now use the same reverse domain filling that we used for getting planar maps for flight planning Now we're going to do reverse domain filling along the flight track so that we can characterize the air mass history and ask the kind of questions that John asked, where is that dust coming from? So it's the same flight track, but now we're going to initialize trajectories along the flight track, a curtain, and we're going to fly those back in time through the model, and we're going to do the same Lagrangian averaging and look at additional air mass history stuff. So this is the back trajectories for that one flight all along the curtain. It's colored red, or tropospheric trajectories are white, boundary layer trajectories are green, and stratospheric trajectories are red. So that curtain that the WB-57 flew on that one day, you can see it had air mass origins of basically the majority of the northern hemisphere. There's clearly some tropospheric air that was tied up in circulations over the Pacific. There's these air mass origins, again, tropospheric, that got into the Asian boundary layer that are likely the source of that dust. And then in the stratosphere, you've got air that's moving eastward and westward because we're in the middle of this sudden warming and things are getting mixed very efficiently. So we have all these trajectories. What do you do with all that information? That's where the Lagrangian averaging comes in. Lagrangian average quantities along these trajectories, map them back to the flight curtain, and then you can start interpreting all those set of measurements. So this is what the Lagrangian average ozone looks like along that flight track. I won't go back to show our original prediction, just our real-time prediction of ozone, but what we've done is sharpen these features associated with that vortex filling. And you can see that the aircraft did a good job of sampling those vortex fillings. And this is N2O, same kind of thing. What we see here is there's this higher N2O up above where the aircraft sampled, but it's interesting. It's very different N2O than what was sampled in that vortex filament. So this is the same kind of thing for carbon monoxide. You can see that just below this sampling during that dusty air mass, there was some higher CO that would be associated with polluted air masses that was in the vicinity. So then we can start, those are just Lagrangian averages of our predictors. We can also start doing statistics, how much of the time was a particular trajectory within the stratosphere, the troposphere, et cetera. So this is stratospheric exposure. You can see that 100% of the air sampled here and here had been in the stratosphere for the last 7 days. But this area right here where we saw enhanced N2O actually has somewhat less, down as low as 60% of the time in the stratosphere. So it had different air mass origins. We can trace this air back to tropical tropopause layer air. So that's transport that we have. The aircraft didn't sample it, but we had tropical tropopause transport that went well into, this is 17 kilometers or so, into the polar stratosphere. And so that's one of those paths of the Brewer-Dobson circulation.
Brad, do you know if that air intrudes within a theta layer?
Yes.
And does that cause anicyclogenesis? Because you're stuffing air into a layer that's already thin at high latitude, and then it kind of has to get thicker?
The way you change the thickness of a potential temperature layer is through diabatic heating.
What about mass injection? Can't you do it that way too?
Just stretching the layer.
Yeah, just if you take, because it's a pressure interval, so there can be a mass intrusion too. That's what I thought you meant.
Yeah. I think that's.
Maybe we're both trying to sort out, there's a real interesting, complete total vertical profile. It looks like the troposphere air came mostly from the swirly, the cyclonic flow near Hawaii. But then somehow on top of that was superimposed a kind of anticyclonic structure
Dusty layer. Yeah.
that came from Asia.
Yeah.
And how does that vertical orientation stack?
That's where we need to, we have the tools to do that with these back trajectories, but again, at this point, this is the first flight we've done this for. So there's a lot to interpret.
Yeah.
Anyway, so now I'm going to focus on this dusty intrusion. So this is the Lagrangian average dust, and you can see that we do have dusty layers down low, but there's this gap in the middle. Now we're looking at Lagrangian average water vapor, and what you see is that the dusty layers were very dry, And in the middle of this is a very moist plume. And the dynamicists in the room are saying, I know what's going on here. So now we're going to look at Lagrangian average convective mass flux along the back trajectories. That moist plume in the middle of those dusty layers had significant, like up to 100 millibars per day of mass flux in that layer. And you've got other areas where you had high mass flux that are kind of just below the trouble zone. So with that, we can go on further and look at some more air mass history diagnostics. And so now we're going to look at what fraction of the year was spent time in the free troposphere. So lower free troposphere, less than 8 kilometers. What we see here is this dusty dry layer spent over 80% of its time in this lower free troposphere, whereas this moist, more dust-free air spent less of its time in the lower free troposphere. What fraction of the air came from the continental boundary layer? This gets back to John's original question. That dusty layer spent anywhere from 20 to 35% of its time in the continental boundary layer. And so we're able to start really slicing and dicing these air mass histories. These are the dusty layers. If you look right here, right above that moist layer is an area where air had spent a significant amount of its time it had continental boundary layer origins. This is what percent of the time was marine boundary layer exposure. So this air came from the marine boundary layer that had spent 80% of its time in the marine boundary layer. This pattern looks just like the convective mass flux. It was convectively lofted into here, but right above there is this air that had continental boundary layer. So this is the two different air mass origins, but all converging to the same place. SP2, the black carbon measurement, was going in and out of this layer and saying there is different processing of the black carbon aerosols between these two layers. One is a moist processing and one's a dry one. And we're able to predict that with a 1 degree model, which is, I think, pretty remarkable. So anyway, this is the marine boundary layer exposure. And then we can also look at how much, when was the last time this air was in the continental boundary layer. So you can see down here, this air in our main part of the dusty air mass, it was 160 hours or so ago that it was in the continental boundary layer. That's that long-range transport. But up here, there's some air that took half as long to get to where the WB-57 was. And that's that real interesting air that's right above that very moist layer. So we're starting to tease out from all those trajectories what these different air mass origins are. And then this is time since marine boundary layer exposure. It's less than 50 hours since that moist air was injected into the altitude of the WB-57 sample. So this is a work in progress. I don't have any conclusions, but I do have a list of further reading, in particular looking at some of these climate intervention topics that I referenced, and then also more details about this reverse domain filling approach. And then I'll end here with questions. This is Thunderdome. This is where Maggie and I spent. I spent 2 weeks and Maggie spent 3 weeks. This was the temperature on February 27th, the day before my 64th birthday, minus 24 degrees Fahrenheit outside of our hotel. This is the WB-57 pilot taking a selfie with Aurora in the background from the aircraft. And this is the WB-57 taking off from Ellington Air Force Base, Elson Air Force Base, and that's the Denali range in the background. One of the days that it was clear, we could see it. So with that, I'll stop and take any questions. Yes?
So, you've done a lot of work with comparing to the RACOMS model that you developed, and I was wondering, to tie it back into kind of the beginning of your talk, is there plans then to seed the model then, to kind of compare to seeding techniques? Is that what RACOMS is being used
So ultimately, I mean, the reason we want to collect these measurements is to evaluate the fidelity of the models, and then so that we could use those to conduct the kind of experiment you're proposing, where you seek them. Right now, RACMs, we don't even have OCS stratospheric sulfate chemistry in the model. So RACMs is really, we're using it as a forecast model. There are other models like WACM, whole atmosphere model, that go all the way up to 190 kilometers, fully resolve the mesosphere, and have more complete stratospheric aerosol treatment. And it is a climate type model. And yes, those could be used to assess the impact of injection of stratospheric aerosols once we have some confidence that the models have skill in the physical processes that they're trying to represent.
Do you know, Brad, if you have any of these filament cases that, where things are not as well predicted? This is fabulous prediction. It's an unbelievable tool. And if so, I mean, what might be the differences that in the processes that led to those structures?
I think that there was, Maggie can correct me if I'm wrong, there was only one flight that we blew. And it was another one, it was not because of a filament prediction. It was because of it was more that we were predicting that gradients were going to be extending down further, lower altitudes than they actually were. And so we weren't able to get high enough up. You know, the forecast skill is enough to put the plane in the right place. I'm going to get back to some of this verification. We have the bulk features okay. These are correlations for the tropospheric, and if we just look at this leg, we have one filament. There's actually much more structure in that than we're actually predicting. So, if we were to look at our forecast skill compared to in situ measurements, for these particular features, it was good enough to get us in the right location, but it wasn't good enough to actually predict the structure of the feature. Because these things there's so much shear deformation in these things that they're generating fine scale structure that our model can't capture. Gerald actually, during the 2022 campaign, did look at, looked at forecast skill as a function of time. So what's our 0 hour, 24, 48 hour, 72 hour forecast skill? Just like in a roll off kind of curve. And we lose predictability, it goes below 60% or so at about 72 hours.
Can I ask just a little bit of a follow-up there? When you deploy the aircraft, are there certain features in the observations you're looking for? So, I'm imagining when one goes to fly through an upper level front in the upper troposphere, one wants to find the -38 air or something at 200 millibars and then fly across it to where it's warmer. Are there such things you can do with this, and does the model allow you to find those initiation points? It looks like it did in this case.
Yeah, so one of the objectives was to target aged air, and so low N2O was the main objective.
Okay.
And I could, the flights that when the lobe was actually over our field of operations, Maggie was doing flight plans that were specifically targeting sampling low N2O within that vortex lobe. Then there's other flights we did that are day-night flights, so you could look at transition chemistry from day to night. And again, those had very different objectives. It was the gas phase chemists that were saying, we want to sample, N2O5 as it goes from day to night, things like that. Yeah, each flight had its own science objectives that we had to kind of optimize with the flight planning team and with the instrument scientists. Very cool.
So when you're flying a flight that has scientists on board, you can do real-time adjustments to your flight path. Is anything like that possible in this?
We did, yeah.
Okay.
There's no scientists on board.
Right,
There's a pilot and a co-pilot.
Yeah. Okay, so were there ever times when you had a forecast and it was just so wildly off and you had to say, no, you need to be over here, or?
There was the one flight that we did where we were heading far north, and we were predicting that we were going to hit into low N2O, but it was actually higher than the aircraft could get. We turned that around earlier because of that. Other flights, the more important role was we're getting real-time data down from the aircraft. And so we're able to, for this flight, for example, we were able to, this was designed, this flight here was, it was zigzagging in the horizontal and it was zigzagging in the vertical to identify it. We did that, we said, we found it, this is where you should focus. And we did that frequently. Yeah.
My earnest hope is that everybody does not want a permanent dim sun. I really hope that's the case. But I'm curious, do you know of any international laws that would bear on rogue actors, rogue legislators, rogue companies,
Yeah.
and limit that, or is there nothing?
This is one of the big issues. So I don't think right now there is any international agreements that talk about rogue actors.
How
And-
about things from doing cloud seeding research?
Yeah, yeah.
There were probably some laws from that that might be applicable. You know, some states
Yeah.
started to sue each other.
Right, and
Because
that's,
it's totally irresponsible to take away
but it's at a,
moisture supply.
it's at a much larger scale.
Yeah.
Those were like, you know, one state would sue another state because you took my precipitation.
You know that green curve that goes up and then goes crashing down
Yeah.
toward an ice age? Can anybody guarantee that that would not happen?
I think that green curve just went back to.
It goes to an ice age, right?
Yeah.
Can anybody guarantee that wouldn't occur?
No, that's why we need to do this kind of research, right? So, and the stuff about rogue actors is a legitimate issue. There's places that are already doing that. So one of the things is, you know, monitoring and being able to detect when that's happening. So I think we've got a class coming in. So.
Yeah, unfortunately we don't have more time for questions, but let's just do another round of applause for the speaker.